evening, friends. Let us look at the preparation strategy. Mostly we will see important question analysis today for analog circuits. And by the way, I am Kiran Kumar, faculty of ESE Engineering Academy. We all know that analog circuits is a little vast. So what I have done is I divided the subject into 4 parts. One is diode circuits, op-amp circuits, BJT circuits, and MOSFET circuits. So generally, if you see for GATE ECE students, you can score from 8 to 10 marks. So you are writing GATE paper for 100 marks, and at least 10 marks you get in analog circuit, so that's a lot of marks, right? In EEE you can expect up to 8 marks, 4 to 8 marks, and instrumentation of late we are constantly getting around 10 marks. So this is my assumption, but let's see the ground reality here. For ESE, ECE around 20 marks. In ESE, you know, in prelims each question carries 2 marks. So at least 10 questions you can expect in prelims paper. ESE mains around 100. That's the same for EEE. For EEE around 12 marks, and in mains around 80 marks you can expect. But what are the extra syllabus for ESE exam? Engineering services exam is 555 timer, JFET analysis, and power amplifier. And what are the prerequisites for this course? The prerequisites for analog is basic 12 standard KVL and KCL are enough. So you can start right away learning analog. But there is a wrong notion for students that EDC is a prerequisite for learning analog, but that's not the case. In EDC we study about the devices, but here in analog we treat every device as a black box, and we are interested only in the terminal behavior. So once we model the device with some equivalent circuit, you can, with basic KVL and KCL, you are good to go, right? And when it comes to prerequisite, I have to tell you that any subject you can start, because these questions students will keep asking. I remember students asking me, sir, which subject should I start while preparing for GATE exam? And I tell them that suppose I remember telling a student, start digital electronics, right? Then he says, sir, these digital gates are actually made from circuits, so should I study circuits? Then I told him, okay, you can start studying circuits. Then he said, no, to study circuits maybe I have to have a strong background on EDC, so should I study EDC, the device physics and all that? I said, okay, if you wish to study EDC, then you can start EDC. Then next day he came to me and said, sir, for studying EDC, should I have a strong background on electromagnetics? Then I have decided this student is not going to start any subject, because it is not what subject you are learning, because every subject has an abstraction. An abstraction means what are the topics, which the parameters of interest, and what are the things that you are not interested of. So that is very important, and this bifurcation is there in every subject. See, for digital electronics I don't understand, because once you make a digital gate, a gate abstraction, there is no circuit there. With a little idea of Boolean algebra, you are good to go. You can start digital electronics. What if millions of such gates, you make it into an ALU or a CPU, a memory unit, and they will introduce some logical attributes to it, and then some instruction set and addressing modes, you are good to go with CO, computer organization. I don't remember much of CO, but computer organization is a beautiful subject. The prerequisite is not digital. You can study how to form digital computers. That's an abstraction, that's a separate subject. Digital electronics is altogether a separate subject. Analog is separate. Every subject has abstractions in it. You have to understand. You just have to start. The choice is yours. The choice is yours. Please. Control systems, I even try to convince the students. See, control systems is a beautiful subject. It's filled with all the plots. Those plots build insights as to what the system behavior is. And control systems doesn't even care if the system is an electrical system or a mechanical system or an electronic system. You can study it, as an individual subject, beautiful subject. Anybody who finishes 12th standard, he can directly go and sit in a signals and systems class. He is good to go there. Signals and systems is altogether a different subject, a different interesting subject. It's individual. It has its own abstractions. Basic 12th standard mathematics is enough. And the same is for every subject, right? If you know little Fourier transform formulas and little probability theory, you're good to go even with communication systems. So my suggestion to you is don't brood on because most of my colleagues will agree with me, because they also would have got phone calls and WhatsApp messages from students saying that which subject should I start. The key is not which subject, the key is you should start. Please start. Every subject has an abstraction. See, if I want to drive a car, I can't tell myself that I have to know the whole function of the car before I can drive it. It is ridiculous. People will laugh. To drive a car, what's the abstraction? To build any skill, I have to know how to move the steering wheel, move the joystick, and how to use the accelerator and the brake. That's important, right? So please, every subject is built individually. Just start it, okay? And this is the ground reality I was talking about. If you see 2023, around 6 marks you have got in EEE, around 10 marks for ESE exam. And for ECE, as I told you, 4 2s are 8, 8 plus 2 is 10 marks for ECE, and around 24 marks for ESE, right? And in 2023, 4 2s are 8 plus 2 again for instrumentation, 10 marks. So analog, in my opinion, will give you a good number of marks, right? Okay, so this is the list I have made out of my experience. Whenever you see a problem, what is the strategy? Rather than strategy, maybe strategy is not a correct word. What should be the mindset of the student the moment he sees a problem, right? Now, you estimate the range of the possible solution. So even without solving a problem, the moment a problem is given, you should be able to estimate what will be the range of that problem. At least the range from say 0 to infinity or from minus infinity to 0, you should be able to estimate the range of the possible solution, right? And maybe this is quite simple, but it's very, very important. You have to focus on the units of the required solution, right? Suppose the units of resistance is in ohms, and the examiner might want the answer in milliohms, or he might want it in kilo ohms also, right? So you please see the units very carefully, right? Focus on the units of the required solution, right? Sometimes what happens is the options given in the gate problem are so widespread. For example, he asks you to find voltage, right? The options are 10 volt, 20 volt, 30 volt, 40 volt. So they are so widespread, you don't have to do the exact analysis. You can just go for approximate analysis, neglecting a lot of things. Suppose your answer comes close to 8, then out of 10, 20, 30, 40, maybe 10 is the right answer. So you can give a shot there. So if the options are widespread, please go for approximate analysis instead of the exact analysis, and eliminate the wrong options so that the leftover option could be the possible solution, right? And there are times where unnecessary data is given, so you can just discard them, right? So please identify unnecessary data given in the problem. So estimate the range of the possible solution. So let me give you a small example here. Now this is a gate problem, okay? Now in this problem, you're asked to find the output voltage here, and there's a big 4 transistor circuit. But in figure, all transistors are identical and have high value of beta, the value of V naught equal to. So this is the question. Even before I solve the question, please see here, this end is ground and this end is phi. So ground is 0 and this is phi. So what are the numbers between 0 and phi? What are the numbers between 0 and phi? 0, 1, 2, 3, 4, 5, right? So these are the numbers between 0 and 5, and look at the options given in GATE exam. Minus 1.8, you don't get between 0 and 5, minus 3.6, 6.2 and 1.8. So hopefully 1.8 is the right answer. So you can solve that problem, but even before, even without solving a problem, if you look at the options, the option itself tells that this voltage which is hanging on between 0 and 5 has to be somewhere between, you know, the numbers 0 and 5. So hopefully 1.8 is the right answer, right? So this is a nice GATE problem. Now focus on the units of the required solution. So I took one more GATE problem here. Calculate the input resistance of the op-amp circuit given, right? So you are asked to find the resistance here. So you can connect a test voltage and take some current and then find it, right? But look at the options given in the GATE exam. Now what is the units of resistance? The units of resistance is ohms, right? So logically, if I assume all resistors to be same value, imagine all resistors are of same value, R, R and R. So you have R by R into R. So R by R square, that's 1 by R, it's not even a resistor. And R square by R square, that's a constant, it's not even a resistor. And R square by R square, that's again a constant. And R square by R, that's R, so that's a resistance. So even without solving, you can simply say, you know, for the GATE problem, you know, this is the option, right? I mean, we can solve it here, connecting a test voltage and, you know, finding a current, and then maybe, since there is a negative sign in all the options, so maybe this circuit simulates some negative resistance, right? It could be a gyrator. Okay. So yeah, let's solve some of the PYQs here. The diodes D1 and D2 in the figure are ideal and the capacitors are identical. The product RC is very large compared to the time period of the AC value, AC voltage. Assuming that the diodes do not break down in the reverse bias, the output voltage at the steady state is. So the examiner wants you to calculate V naught here, right? So he has given two diodes here. This is a previous GATE problem. So you can see, say during positive cycle, the diode is on and we know the polarities of the capacitor will come with the direction of current. Say the capacitor charges to some peak value here, Vm, and it charges to the peak value Vm here, assuming the diodes are ideal, right? So now you can apply a small loop equation here to finish the problem. So plus to minus, so plus Vm minus Vm plus V naught is 0. So your V naught, you can cancel this, is 0 volts. So 0 is the solution to this problem, right? So during positive cycle, these two diodes are on and the polarities for the capacitor will come with the direction of current. So when you apply a loop equation here, so you can see here plus minus and minus plus, so they naturally cancel each other. V naught is going to be 0 volts, right? Yeah, in the circuit shown, Vs is a square wave of period t with maximum and minimum values 8 and minus 10 given, assuming the diodes are ideal and R1 and R2 are 50 ohms. So this guy is 50 here and this guy is also 50. So the average value of V1, the average value of V1 or VL, I think this is VL, which is the load voltage, right? So how do we solve this problem? So during positive cycle, we know that the diode is off, so it's a simple voltage divider. So in a voltage divider, if two resistors are of same value, you have 8 volt here, so you're going to get half of it, right, 4 volt. Now what if I give a negative voltage of minus 10 here? The diode is going to get on and your output is going to follow the input. So for the negative cycle, the diode is going to get on. So if you give minus 10, your output is also going to be minus 10. So how do we sketch the output? To sketch the output, during positive cycle, you're going to have 4 volt, and during negative, you're going to have minus 10 here. And we know the average is going to be somewhere in the middle, that is the V average, right? And what is the middle point here? V average is a point where this voltage and this voltage are going to be same, right? So 4 minus V average is going to be V average minus of minus 10. So 2 times V average is going to be 4 minus 10, it's minus 6, so V average is minus 3. And of course that's logically correct, because if you have minus 3 here, then 4 minus of minus 3, there is a 7 volt peak here, and then minus 3 minus of minus 10, so that's again 7 volt. So the V average is going to be minus 3 volts. So that's the right answer. Now this is a good problem. This is again a previous paper question. The figure shows a half wave rectifier with a 475 millifarad. So here it's given micro, so this should be microfarad filter. The load draws a constant current I naught of 1 ampere from the rectifier. The figure also shows that the input voltage Vi is a triangular waveform, and the output voltage Vc, and the peak to peak ripple voltage is U. Oh, he wants a ripple. So the input voltage Vi is a triangular wave with an amplitude of 10 volts and a period of 1 millisecond. So the huge data is given. Now he wants the ripple voltage here, the small bubble thing here, this ripple, the magnitude of this ripple voltage he wants. Now how do we solve this, right? Now let's apply the law of conservation here. So what you lose in this, you're going to gain here, right? Suppose here, remember, the diode is off and the capacitor has to discharge, right? So if the diode is off, the IDC, so what is the law? The law of conservation of charge says that Q lost is Q gained, right? Q lost is Q gained. So what you lose here, you're going to gain here. So what is Q in terms of current? What is Q in terms of current? I think it's IDC into T, right? I into T. And what you gain in this duration, Q in terms of voltage, because the ripple is actually a voltage. So what is the charge in terms of voltage? I think it's C into V. So he wants the ripple voltage VR. So VR is nothing but IDC into T by C. So it's a simple substitution problem. And what is IDC? IDC is going to be the DC current 1 ampere into T. There is no T given. 1 millisecond is given by C, which is 475 microfarad. So micro is 10 power minus 6, so it's around 1000 by 475. So imagine 1000 by 500, it should be 2, so 475, so maybe 2.1, something like that. I'm not quite sure. Sorry, this is not ampere, it is volt, it is voltage, because ripple is not, it is volt. So I repeat, the law of conservation says that, you know, what you lose here is what you gain in this duration. So charge lost is charge gained. So charge in terms of current is I into T, and charge in terms of voltage is C into V. He wants V, so VR is IDC into T by C. Fine. So this is again a gate problem. Now in this gate problem, the examiner says he's got an asymmetrical periodic pulse train V in of 10 volts amplitude with an on time of 1 millisecond and off time of 1 microsecond is applied to the circuit as shown in the figure. The diode is ideal. Now the difference between the maximum voltage and the minimum voltage of the waveform. Now please understand that this circuit is a clamper, right. So what happens in clamping is the peak to peak voltage will always remain same, right. So you are restoring a different DC value, but then the peak to peak will always remain same. So the output peak to peak and the input peak to peak both are same, so you do not have to solve this problem, it is already given here 10, and this is unnecessary data here, 1 millisecond on time off time, you know, just to confuse you, and all these capacitors and all that. There is no need. Once you have identified that this is a clamper, the peak to peak value of output and the peak to peak value of input both are going to be same. So the question says it is 10, so the answer is also 10. So this is the answer. So the difference between the maximum and minimum voltage of the output waveform is going to be 10 volt, right. Okay. Now this is a current mirror circuit. In the silicon BJT circuit shown below, assume that the emitter area of transistor Q1 is half that of transistor Q2. The value of I naught is, see, when I started this listing out what are the things you have to remember, I even told you that you can always go for approximate analysis if the options are wide, right. So one is 0.5, the other one is 2, 9.3 and 15. So they have much difference, right. But you can see the beta value is 715, that is a large value. So you can simply take beta infinite and do it. So you will get a quick answer. Maybe you may not get these options, but your options are going to come closer. So please try to do approximate analysis. If the options are wide, you do not have to do exact analysis, because the exact analysis takes time. I mean, that is also easy, but it takes time. See, this is I naught, and since this area is 2 times of this is almost like 2 transistors in parallel. So when you have 2 transistors in parallel and you have I naught, a single transistor here is going to be I naught by 2. And what is this current and this current? This is going to be I naught by, the IB is going to be IC by beta, it is I naught by 715. So this is I naught by 2 into 700. So my cry here is these values, if you calculate on the calculator, it takes time, so you can actually avoid this, I am saying, since the options are here. So if you avoid them, this is I naught by 2 and this current you are avoiding it. So this is already I naught by 2, and here you have 0.7 volts. So minus 10 plus 0.7 is going to be minus 9.3. So what is the solution here? I naught by 2 is going to be 0 minus of minus 9.3 by 9.3 K. So this is 1 milliampere, 1 into 2 is 2 milliampere. Oh, the examiner also has given approximate value only 2 milli, But I think if you take these two also, you may not get 2 milli, you might get 1.999 something like that. So by taking these values, you're just putting yourself into trouble, 1.99 like that. So there's no need, I just neglected this, but I still was able to get 2 milliampere here, right. So option B is the right answer. Now consider the circuit shown in the figure, assume VB1 and VB is 0.7. So you have, the examiner has given 0.7 here and 0.7 here. So 0.7 plus 0.7 is going to be 1.4, right. So you have 2.5, 0.7 and 0.7, so this is 2.5 minus 1.4, so that is 1.1 volt here. So he wants this voltage Vc2. So if this current is IB for this transistor, this is going to be beta times of IB, and beta is 50, so 50 IB. So let's calculate Vc2 right away, 0.5 volts. Yeah, 5 into 0.1 is 0.5, so I think 0.5 is the right answer, so it's 0.5 volt. Now you can see each transistor in the Darlington pair has HFE, HFE is beta again, beta equal to 100, the overall HFE of the composite transistor neglecting the leakage current. So how do you solve this? This is a simple Darlington pair. He wants the ratio between the overall current here and the overall current here, the ratio between the overall IC and IB, which is the HFE. HFE is the forward current gain. So he wants IC by IB. So how do we calculate IC by IB here? And each transistor has beta equal to 100. So this is given in the problem. So each transistor has beta equal to 100. So how are we going to solve this problem? Okay, so if this is IB, then what is the collector current? It is 100 times of IB. And what is the emitter current? Emitter is beta plus 1 times, so that's 101 times of IB. So if this is the base current, then the collector current is going to be beta times of IB, which is 101 times of IB. So what is the total IC now? This total IC is split into these two. So it's the total IC is going to be 100 IB plus, how much is this? 100 into 101, 100 into 101 times of IB. So what is IC by IB? IC by IB is 101 into 100 plus 100, so it is going to be 10100 plus 100, it is going to be 10200, 10. So this option D is the right answer for this, because this is beta IB. This is beta into beta plus 1 times of IB. So your IC is going to be beta IB and beta into beta plus 1. So it is beta square plus beta, and this is again a beta. So this is beta square plus 2 beta. So beta is 100. So 100 square is 10,000, and beta is 100. So 100 into 2 is 200, 10,000 plus 200 is 10,200. 10,000 plus 200 is 10,200. So that's the solution, right? So these are all GATE previous year questions. A Darlington stage is shown in the figure. If the transconductance of Q1 is GM1 and Q2 is GM2, then the overall transconductance is. So he wants the ratio between the overall IC and the overall VB here, right. So VB is the voltage from here to ground. So this is the VB given, and this is IC, right. Now these are the 4 options given, but how do we solve this? And what is GM1 and GM2? GM1 here is the transconductance of Q1 transistor, and GM2 is the transconductance of Q2 transistor. So let me define GM1 here. So GM1 is IC1 by VB1, and GM2 is IC2 by VB2. So how do we solve this? If you remember, if the input is given at base and the output is taken at emitter, these circuits are, this topology is called an emitter follower, and the gain of emitter follower is usually 1. So what do you mean by emitter follower? The output at emitter follows the input, right. So this voltage will almost follow this. So if you give VB here, the gain from here to here is going to be the same VB. So this VB is actually your VB2, and this IC is your IC2, and IC2 by VB2 is GM2, so GM2 is the right answer. But in some textbooks it is given 0.5 GM2, but that is wrong, right, because this is an emitter follower, the output at emitter follows input, and moreover there is a mismatch here. If you can see, the output resistance of Q1 is alpha by GM, and the input resistance here is R pi. So it's almost like a voltage divider where you have ohms here, ohms, alpha by GM is ohms, and there is kilo ohms here. So whenever you apply any voltage, it's going to manifest here. So yeah, if you want 0.5 GM2 in the problem, then what change should I make in this circuit? Because some textbooks call this 0.5 GM, which is wrong, but if you want 0.5 GM, what you have to do is don't connect this point to the base terminal, you connect it to another emitter terminal. So then there will be matching between the two stages here, but here there is a mismatch here. So but if you draw something like this, like in differential structure, so here there is alpha by GM and alpha by GM, so you have alpha by GM and alpha by GM, this signal is going to get half here, is going to get half. But not in this problem. In this problem, the output at emitter follows input, so this is an emitter follower, so it's going to be GM2. Now the voltage gain AV of the circuit given below. So how do we solve this problem? This is a previous year question. Now if you understand this topology here, this is a shunt feedback, a voltage shunt feedback, and this is similar to the circuit which we have seen in op amp also. In op amp, if you have a feedback resistor of 100K and an input resistance of say 10K, so there is V in here and V naught here, V in here and V naught here. then we directly know the gain of this V naught by V in is going to be minus 100k by 10k. It is approximately minus 10. It's approximately how much? Minus 10. If you take a mod value, then the voltage gain is getting close to 10. So that's the solution. But how do we arrive at that? Because the examiner has not given an op amp, he has given a BJT here. Because whenever there is negative feedback, what happens whenever there is negative feedback? When there is negative feedback, the input terminals, so the voltage between the two terminals is going to converge, and the voltage at this terminal is going to appear here because of the feedback by backtracking, and that is something we lightheartedly call it as virtual ground, right. So what is virtual short? Whenever there is a negative feedback, these two potentials, they converge, right. This potential appears here. So you can apply the same technique here, and look at the unnecessary data here. In this problem, did I give you any supply voltage here? No, I didn't give you any supply. So this supply is an unnecessary data, right. You can take the supply voltage and do DC analysis and AC analysis, and finally your answer is going to come close to minus 9.5 or something like that, but that's not needed, right, because I didn't give any supply here. This supply is also not needed, right. Did I give the gain of this op amp? No, I didn't give. So this is again an unnecessary data. You don't need it. 100, 200, 300, it doesn't matter. Your answer is going to come close to minus 10, right. And this load, I didn't connect any load here. And this load is again an unnecessary data. I mean, you can take that value also, but your final answer is going to get close to 10. And look at the beauty here. The examiner puts a symbol here, right. So what do we call this symbol? This symbol is called the approximate value. So the examiner himself says, don't do exact analysis, because if you do exact analysis to this problem, naturally it takes around 2 pages to solve, and you can still make it troublesome by splitting this resistor using Miller and all that. So that's crazy, right. So if you do that, it becomes too cumbersome, right. Please apply Miller's theorem only for capacitors, not for resistors. So for resistors, whenever you have resistors in feedback, we never solve this problem by Miller, we solve it by virtual ground. So the same thing you can do here also. So it's minus 100k by 10k. Capacitors for AC analysis, you can replace them by short. So this guy is short, this is almost going to converge to 0. This is the small VB, but 0.7 is capital VB. 0.7 is DC, we are not doing DC, we are doing AC here. So this voltage is almost going to converge to 0. So this is going to be 0. Here op amp draws no current. Here the base current you can neglect, the base current, and this is the entering current and this is the leaving current. So you can take I1 and I2, just like how you take I1 here and I2 here. And how do we apply KCL? KCL. The current entering is current leaving. So V in minus 0 by 10k is 0 minus V naught by 100k. So that's it, V naught by V in is going to be minus 100k by 10k, it's minus 10. So minus 10 is a right answer for this problem. You don't have to do the exact analysis, go for approximate. The examiner also wants that approximate, and all this is unnecessary data, right. No beta, we don't need the resistors, we don't need the supply voltage, we don't need those capacitor values and all, right. Now again, this is another gate problem. So how are we going to solve this? Just go through the question. In the circuit shown below, the silicon NPN transistor Q has a very high value of beta. So whenever somebody says a high value of beta, you can always neglect the base current. The collector current and emitter current both are going to be same, right. So if this is IC, this is also going to be IC. So that what it means by high value of beta. And then the required value of R2, the required value of R2 is asking, and IC, oh yeah, IC is given 1 milliampere. So what is 1 milliampere into 500 ohm? 1 milliampere into 500 ohm, 1 milliampere into 500 ohm is going to be 500 milli, is going to be how much? 500 milli, and since it is silicon, we can take 0.7 volts here. So 0.7 volts is again 700 milli, 700 milli, and this is 700 milli, this is 500 milli. So 500 plus 700, it's 1200 millivolt. So this is going to be 1.2 volts. So 700 plus 500 is 1200 millivolt, 1200 millivolt. So what is 1200 millivolt is 1.2 volt, right? So what is the value of resistance by Ohm's law? Ohm's law says that resistance is voltage by current. So since a large value of beta IB is neglected, this current and this current both are going to be same. So resistance is voltage divided by current. Current is 3 minus 1.2 by 60K. So 1.2 by 3 minus 1.2 is 1.8 into 60. So how much is this? 1.2 by 1.8 into 60. So how much are we going to get? So I think there is a slight mistake in the problem, because okay, 6 2s are 0.3, so 1200 by 0.3. So what I assume in the problem is there is a mistake, there is a printing mistake here. Maybe I am just assuming that this is not 50. So I have a gut feeling that this is not 500, it should be 50, because if it is 50, then my answer is coming close to the options, because if this is 50, you get 50 millivolt here, this is 700 millivolt, 700 plus 50 is 750, so that is 0.75 here. So 0.75, and what is the current here? So R2 is going to be, so there is a printing mistake here, I think this should be 50. So let me try now. So R2 is 3 minus, R2 is the voltage, 0.75 by 0.75 by 3 minus 0.75 divided by 60. So it is 0.75 divided by 3 minus 0.75 is going to be 2.25 into 60. So 7 3s are 21. So 60 by 3, 60 by 3 is 20K. So 20K is the right option. So I think I have a feeling that this is not 500, it should be 50. So then if you multiply this by 60, so it goes 3 times, so 60 by 3 is going to be 20. So that is the correction, that is fine. Oh, this is so much written here. Consider the common collector amplifier in the figure. The bias circuitry ensures that the transistor operates in the forward active region, but has been omitted for simplicity. Let IC be the collector current, VB is the base emitter voltage, VT are not what does he want? Which one of the following conditions ensure a constant small signal? He wants voltage gain for a wide range of values of Re. For a wide range of values of Re, he wants the voltage gain, right? But yeah, so this is the circuit. So he says which condition gives you a constant voltage. This is an emitter follower, so the gain is almost 1, and we know this Re has to be a very large value, but then see, I will give you a simple logic here. He is referring to Re, but in these two options there is no Re at all. He is mentioning about Re, but in the options there is no Re at all. So that itself tells that these two options are is something that he does not want. There is Re here, and he is referring to Re in the question, and here he says GM Re is much less than 1. That means he says Re is much less than this 1 by GM, so this Re is very less. So what happens, this Re is very less, is almost 0, this V0 is going to touch the ground now. So that is also wrong. So that means the leftover option is the possible solution. Of course I will try to solve it, but I am just telling you by logic. He is mentioning about Re and he does not mention here. So these two are wrong. This option says that Re is a very small value and this goes close to the ground, so that is also a wrong option. But let us solve this problem. So I am just expecting this could be the possible solution, right. So how do we find V0 by Vin? Here you have IE here there is a small Vb, because in small signal analysis all the parameters you have to write with small letters, right. So what is V0? V0 is going to be IERE, and what is Vin here? Vin is Vb plus IERE. So even if you draw the small signal model, replace the transistor, this is exactly what you are going to get. And what is V0 by V? Now you divide both numerator and denominator by IE, divide by IE. So you are going to get Re by Re plus Vb by IE is alpha by Gm. Now what he says is, to get, suppose you want this output to be close to 1 because it is an emitter follower, then this Re should be much greater than 1 by Gm or alpha by Gm. And what is Gm? Gm is IC by Vt. So if your Re is much greater than 1 by Gm, it is Vt by IC, 1 by Gm. So Gm into IC should be much greater than Vt. Gm into IC, yeah. So of course logically that is the only leftover option, because the other options does not make any sense. He is referring to Re and there is no Re here, and here Re is a very small value. So this option could be the possible solution. Now please go through this gate question. For the common collector amplifier shown in figure, the BJT has high beta, negligible Vc, and Vb is 0.7. The maximum undistorted peak to peak output voltage. Now what do you mean by undistorted output peak to peak voltage? So he wants a peak to peak voltage of this V0, this is the DC value, and look at the logic here. This is ground, and what is the voltage of ground? That is 0, and here you have 12. So your signal is going to swing between 12 and 0 with some DC value, but what is the clue here? When you want to draw a sine wave, you cannot draw a sine wave like this. This is not a sine wave. A sine wave should have symmetrical swing, the positive peak should be equal to negative peak. So this is a wrong sine wave, right? You cannot draw a sine wave which is like this also. This is not a sine wave. So let's choose a DC value where you can have symmetrical swings, right? Okay, let's solve the problem. This is 12 volt, you have 5K and 10K, right? So 12 is divided in a ratio of 1:2, 1:2 by voltage division, because voltage division will usually give you the fraction of the input voltage. So it's like 1:2, so you have 12 volts, so hopefully you have 8 volt here, 2 portions here and 4 volt, 1 portion there. So 8 minus 0.7 is going to be a DC of 7.3. Now you tell me, for 7.3 who is near? Who is near? Is 12 volts near or 0 is near? What is 12 minus 7.3? I think 12 is near, because if you have 12 volt here, 12 minus 7.3 is 8, 9, 10, 11, 12, right? So that's 4.7. So you have 4.7 here, right? So 4.7, this is near, so you can have a negative 4.7 also. But the negative portion can go till 7.3, but then we don't want a sine wave like this. So the logic says is the positive portion has 4.7 and the negative has 4.7. So 4.7 plus 4.7, because he wants the peak to peak value. So it is 2 times of 4.7. 2 times of 4.7, it is 9.4 volt. So 9.4 is the solution to this problem. So this is the maximum undistorted peak value. What if you take the peak value of 7.3? So you might get a large negative, but your positive is going to get clipped. Your positive is going to get clipped, right? So whenever you want to draw a sine wave, remember a sine wave should have symmetrical swings. Positive peak should be equal to negative peak. So that is very, very important. So this is another gate problem. In the equivalent circuit, the two BJTs are biased in active region and they have identical parameters with beta much greater than 1. The open circuit small signal voltage gain. Now I told you when we talked about the resistance reflection rule for BJT, whenever the base and collector terminals are shorted, you can replace this with a resistor here which is equal to alpha by Gm. And here you have a transistor. Now this is a common emitter amplifier. So what is the gain of a common emitter amplifier? The gain of common emitter amplifier V0 by Vin, or if you want you can take an IC here and VB here. So for AC analysis, please take small letters. So V0 is going to be minus IC into alpha by Gm and Vin is VB. So what is IC by VB is Gm minus Gm into alpha by Gm. So Gm gets cancelled, minus alpha. But he says beta is much greater than 1. If beta is far greater than 1, then alpha is 1. So minus 1 is the answer. So the voltage gain is close to minus 1 or minus alpha specifically. So or you can, if you don't want to convert a transistor into a resistor, that's the shortcut, you can do this by small signal model also, right? So you can take 2 transistors, so that takes time, so you can do it, right? Okay, so I think we are running short of time. So again I am repeating, just to start any subject that you wish, or you can write all the subjects on a piece of paper, call your little brother or little sister, close their eyes and do inky pinky ponky, and finally you find some subject which is of interest to you, please start, okay? and every subject has abstractions. So you can you are good to go, right? What is needed as a prerequisite for any subject, in my opinion, is common sense. You have common sense, you are good to go, you can start any subject of your wish, right? So best wishes to you, and in my next video I will solve the other problems of which are left. Okay, so I think my cameraman says there's still 1 minute left, so maybe I can solve one more gate problem. Okay, yeah. In the circuit shown, transistors Q1 and Q2 are biased with some current here. This is the collector current to emitter current, the thermal voltage is 26 millivolt, the magnitude of the voltage gain. Yeah, I mean the previous problem we did the same thing. So when in AC analysis, when you short this and this for AC analysis, this one is also the same thing. If the base and collector terminals are shorted, then you can have alpha by GM here. So you can have alpha by GM at the emitter terminal. So this is V in and V naught. So what is V naught by V in? V naught by V in. So what are the resistors in the numerator? 1K. And imagine IC here and IC here. So this is alpha by GM by alpha plus 1 by GM. Alpha alpha gets cancelled, minus GM RC by 2. So this is the solution. So what is GM? IC by VT. So GM is IC by VT minus 2.6 by 26 milli by 2 into 1K by 2. So this is 1 by 10, 2 into 10 is 20. So what is 1000 by 20? 1000 by 20. So 0 0 cancel, 2 goes 5 times, so minus 50. So minus 50 is the solution to this gate problem. So you can do this by small signal model as well, right? Okay, thank you all, my best wishes to you. So we will see some more questions in the next video, right? Good luck.
Wherever may be your present journey, but if you decided for your goal, whatever may be your present position, but if you opted to reach higher altitudes in the life, however may be your present duties, but if you choose to find the joy of working, whatever may be your present circumstances, but if you determined for your success. Yes, you rightly heard it. ECE online platform raises you much more than what you can think. This platform provides pre-recorded and online lectures which you can access around the clock. You can prepare for the various competitive exams like GATE, ESE, PSUs and other state service exams, mainly in the English, Hindi and Telugu languages. Hope you'll all going to make ECE online platform as a part of your success story. ECE Online. Learn anywhere, anytime.